So I actually have my video recording from this class from last year too. All right, so we're going to be looking at sequences in series, or infinite sequences in series. So the first thing that we're going to look at tonight is actually what is a sequence, what is a series, and then starting on Thursday's class and going forward, we'll actually start looking at the calculus and how those do it and how we actually prove certain things about sequences or series in that situation. So a sequence is just basically a list of values. So we have a first term, second term, and so on. A sequence does not have to be actually numbers. We're only going to be dealing with numbers, but a sequence can be anything that is in order. So letter grades are a sequence: A, B, C, D, E, or A, B, C, D, F, things like that. That's a sequence. Birth dates and years and stuff like that. Those are all sequences. So anything you can put in order would be considered a sequence. We're obviously going to be dealing with numerical sequences, so this way we can do some calculations with them. When you write a sequence, there's a few different ways that we can write it. We have the set notation with the A1, A2 all the way on, and the 3 dots just means that sequence continues going forward. We also can have it marked as A to the N, or A to the nth term of A. And what that shows, that would be the formula that I'm using to calculate or come up with the sequence. And the other way we can see it is the same thing, but with n equals 1 to infinity on the outside, because sometimes sequences don't necessarily start at 1. They could start a little bit later, depending on where that function comes into play. And we're going to see how those work in a second. So here is a couple different examples. So you can see this is the set of them. So you have 1/2, 2/3, 3/4, 4/5. And the function that I came up with those was n over n plus 1. So this is one way to write a sequence. We also can just write the function as a to the n. There we go. A to the n equals n over n plus 1. And we also can have the same one over here with the n equals 1 to infinity, because obviously 1 would work in that situation. Here's another sequence. This one's just a little more complicated one. It also has an alternating value, so we have -1 to the nth power. So this way it's alternating signs. And depending on what that is, so if I wanted to start off with a positive term, I could do n minus 1 up there, or I could do n plus 1. And that would give you your positive value to start instead of a negative value to start. And then the n plus 1 over 3 to the n. So we get our sequence as -2/3, 3/9, -4/7, 5/81, and so on and so forth. We don't necessarily have to have them just with fractions. You can do them with roots. You can also do them with trig functions, cosines. So any of those, the real key between it and why it's a sequence is that the n value there changes, goes up, and that's what produces the sequence of values. All right. Can everybody read that? It's smaller on my screen. I'm not sure on your screen.
It's pretty small to read.
All right. Okay, let's see. I don't know. Nope, that's not going to work. All right, so we shall try this way. And I'll just move things up. Can you see that now? Is that better?
Yes.
Yeah.
Yes, that's clear.
Okay, so we've got this sequence. It's 3 to the 3/5, comma -4/25, 5 to 1/25, and so on and so forth. What we want to do is we want to come up with a formula or a general sequence of that term. So we look at the fact that we have a to the 1 is 3/5, a2 is -4/25. So that 1, 2, 3, those are going to be my n values. So now I've got to come up with how am I going to set up my equation to get my negative sign, my numerator, and my denominator, all using the same n value. So if we let's look at that first piece there, the sign. So I start off with a negative or a positive, and then I have a negative, positive, negative, positive. So if you remember what I just said a second ago, to get the positive to start first, I would either do an n minus 1 as my exponent or n plus 1. You could do either direction because that's going to give you either -1 to the 0 first, which would be positive, or -1 to the second power first, which would also be positive. So if we look, let's pull this up a little bit. So you can see my equation down the bottom here. So on my first piece right there, I have the -1 n to the negative or n minus 1 power. That's going to be my first piece. Now, if we look at my numerator, I start off with 3, and I'm going up by 1. So it's 3, 4, 5, 6, 7. So the only way to get 3 from that first term would be 1 plus 2. And if we look, if I do 2 plus 2, I get 4, 3 plus 2, I get 5, 4 plus 2 gets 6, and so on. So my numerator is n plus 2. Is going to give me that term going forward. Does those two pieces make sense?
Yeah.
All right. So now the bottoms, I go 5, 25, 125, 625. So those are powers of 5. So that's where the 5 to the nth power comes into play. So each of this function right there, that's going to create my sequence. So anytime we have a set of numbers, we can, not everyone, but most of them, we can actually set up a function for to come up with those values. And what that's going to allow us to do is to do more of those calculations on down the line. All right, let's look at some sequences that don't have equations. And let's go a little bigger. So remember, I said anything can be a sequence. So here's one, the population of the world as of January 1st in every year. Now that's a sequence. It's numerical, but it's not something I can come up with an equation for. We can come up with an equation to estimate it, but it's not going to give me the exact values at that point. If we let the sequence be the nth decimal place in the letter E or pi, we could either do either one of those. It's a sequence that continues going. Same thing with pi. It's going to go and it's never going to repeat. However, there's no way to come up with a function or an equation to calculate that. That's why E and pi are both irrational numbers, because there is no formula that can come up with that value. We can estimate it, we can get it close, but we can't come up with one that comes up with the entire value. The Fibonacci sequence is another one that's really famous. There actually is a formula for it, but it's a recursive formula. It's not a formula that's going to give you every value. Recursive means I need to use the values previous to it to come up with that. So in the Fibonacci sequence, I have my first term's 1, my second term's 1, and then it goes 2, 3, 5, 8, 13, and so on. So we're adding my first two terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. That's why it's recursive, because I need to use the previous terms to find it. So I can't tell you, give me the 25th term of the Fibonacci sequence without you doing all the 24 before that term. And when we're looking for a formula for it, we're looking for one that I can say, give me the 25th term, and you can just find it. So the Fibonacci sequence, you actually would have to do them all because it's a recursive formula. Does those make sense?
Yeah.
All right. Yeah. All right. So the next thing we're going to look at is actually figuring out how to determine if the sequence basically converges to a specific value or if it goes off to infinity and whatnot. So this sequence, if I have n over n plus 1, if we graph it, you'll notice that this is on a number line. It's starting to get closer and closer and closer to 1. And if we graphed it on a graph, you can also see that it's getting closer and closer to that value of 1. And if we think about it, this value right there, if no matter what number I plug in, it's never going to go above 1. because the bottom's always going to be one higher than the top. Even if I did 1,000,000, it'd be 1,000,000 over 1,000,001, which isn't 1. It's getting closer and closer to the value of 1, but not exactly 1 in that respect. We can set up our sequence as a sequence of points. So we would just put the n value as the x terms and my answer for the sequence as my y values. And that would give me the graphical representation of my sequence. So when we're looking at the graphical representation of those, we're looking at the limit as it's going off to infinity. So we're trying to figure out what that value is going to. So in this case, the one we just did, that limit of n over n plus 1 goes to 1. So as I get closer and closer to infinity, the value is getting closer and closer to 1. And since we can never hit infinity, we never actually hit the 1, but that's why we're looking for the limit as it goes to there. And in general form, it's just the limit of a to the n goes to the L, and whatever that L happens to be. They don't all have to go to 1 or a value. They can be divergent, which means they go to infinity. So if I can make it go to a specific value, I have a limit, and we say that it converges. It doesn't necessarily have to converge to 1. It can converge to 2. It can converge to 0. It can converge to a lot of different values. If it goes to infinity, we say the sequence diverges or is divergent. So those two terms that you're going to hear a lot when we're looking at the terms, because that's really our goal is to figure out if the sequence is divergent or convergent when we're looking at them. So these two sequences, if we look at them, this one here goes up and it comes back down. It looks like it's going to that specific value, that limit. And the second one also, even though it oscillates back and forth, it's still starting to get closer and closer to that limit. So both of those functions, or both those sequences, would be convergent. They do converge to a specific value. So it says for every e, there's a corresponding integer of n that says that as long as n is greater than, basically, as long as the difference between them is getting smaller, it's going to converge to a specific value, is basically what it is. So as long as those differences are getting smaller and smaller, it's converging down to a specific point. And eventually, it should get to 0. So that's what this is. It's as each of those points is getting closer and closer together to the limit in the middle there. So the difference between the 2 points are getting smaller and smaller. Another way to look at it is if you look at the external, the above and below, the values are going to get closer and closer to that piece in the middle. The difference between those two is known as a squeeze effect. It's squeezing between the two values there. All right. Yeah, we basically just talked about that one. Yeah, and that's the one. If it's going big, it's going to be, if it goes to infinity, then the sequence is divergent. You actually can diverge to infinity. You also can diverge where it jumps back and forth. So we can have values that don't actually diverge to infinity, but that also diverge because they don't jump to a single point where they're going to go positive and negative, positive and negative. So each value doesn't actually come to a place. So we actually can have divergent to infinity or just a divergent function. These will make a lot more sense when we start looking at some problems too. All right, last thing before we start looking at some examples. The limit laws of sequences. So these actually you've seen before. They're basically the exact same as the limit laws when you did the differentiation. We can split things apart. So the limit of a to the n plus b to the n is the same thing as the limit of a to the n plus the limit of b to the n. So you can split the addition apart. You can split subtraction apart. I can pull out any constants and just deal with the function. For multiplication, I can split the multiplication apart to the limit of each piece. Same thing with division. I can look at the limit as the top goes to infinity, look at the bottom goes to infinity. And the same thing with powers. I can just look at that limit and just take the power to the limit. So if I have a function that's going to 1 and I'm going to have a constant in front of it of 3, it would just go to 3. I would just multiply it by it. So this makes our lives a lot easier since we can split them up. We can look at them in pieces instead of trying to look at it as the whole thing, which sometimes makes our lives a lot more complicated. That's that squeeze theorem I was talking about. We have two functions that would squeeze into this value in the middle, and it does go to a specific limit. Theorem 6 is a little important. So theorem 6 says if the limit of the absolute value equals 0, then the limit of that function equals 0. So when we're having functions that have that negative value in front or that value that's going to jump back and forth, if I look at the limit of the absolute value, if that goes to 0, then the other function automatically goes to 0, the one that I originally had. So if it's bouncing back and forth, but as this bounces back and forth, it's getting closer and closer to 0, it's going to converge to 0, and I know that's the value there. If it bounces back and forth, but it doesn't converge to 0 when I get rid of the sign, then it doesn't actually converge and it goes to infinity. All right, let's look at a couple examples and use those. All right. So in this one, we've got the limit of as n goes to infinity of n over n plus 1. So actually, I'll make this a little bigger. Can everybody see that? Or do I need it bigger?
That's fine.
That's fine.
Okay.
That's it.
All right. All right. So we've got the limit as n goes. So if you remember when you were doing originally differentiation, one of the tricks that we had to figure out limits, especially when we had like n, if you do the limit as n goes to infinity, that's going to infinity. That's not really going to help me. But if we divided everything by the highest power of n, so in this case, I'm going to divide every piece by n. So if I divide every piece by n, I get 1 on the top, and then I get 1 plus 1 over n on the bottom. And now I can look at the limit of each one of those goes to infinity. So the limit as n goes to infinity of 1 is 1. So that's 1 plus 0. So the limit of this function actually goes to 1. And we had already actually saw that function a little bit earlier when we did, that's the fractions. It's 2 over 3, 3 over 4, 4 over 5, and so on and so forth. It looked like it was going to 1. This is how we'd actually prove that it converges to 1. So we just divide them all by n in this case. Here's another one. So we want to figure out if this function is convergent or divergent. So we're going to do the limit again. And we have n over the square root of 10 plus n. Now in this one, I'm going to take and divide them all by n. So I have n divided by n, which is 1. And then the 10, I'm actually dividing by n squared. Why am I dividing by n squared and not n?
Because it's under the square root.
Yeah, so if there's an n on the outside, to put it under the square root, I have to square it. So that's where the 10 over n squared comes from and the 1 over n. Now, each of those pieces down the bottom, 10 over n squared, that's going to 0 because the numerator is getting big. 1 over n is going to 0. So that bottom is going to the square root of 0, which is 0. So as the denominator is getting closer and closer to 0, that means my function, or in this case, my sequence, is going to infinity. So this one diverges because it's going to infinity. Next one, I have the limit of n goes to infinity of ln of n over n. Now in this situation, if we look at it, both the numerator and the denominator are going to infinity. So because ln of infinity is infinity, n is infinity. So when we look at it, we have to use L'Hopital's rule for this one, but we can't just necessarily do it directly to a sequence. However, we can do it to a function. So if we look at it as a function of x, ln of x, we do the derivative of it, and that's what L'Hopital's rule is. We do the derivative of the top and the bottom. It becomes 1 over x, and the derivative of x is 1. So now we're doing the limit of that one. So the limit of 1 over x goes to 0, and the 1 stays there. So this function goes to 0 as the limit as x goes to infinity. So therefore, by the theorem that we looked at, that the function is going to be the same as the original sequence. Since the function goes to 0, the sequence also has to go to 0. So that's how we can start using some of those other rules that we had in previous sections, especially with L'Hopital's rule. We use that quite a bit actually with these. So this one converges, and it converges to 0. Does that one make sense? Question? All right. Next function sequence we're going to look at. And if you're wondering why I'm not writing, I forgot my computer at home, so I can't write them down. So that's why the solutions are there, because I had to cut and paste. So we're going to look at the sequence -1 to the nth power. So now, if we look at this one, -1, +1, -1, +1, -1, +1, -1, it just keeps bouncing back and forth. So this one doesn't approach a number. So the limit of this one does not exist. So it is divergent. And if we think back to what we were looking at with the, this is one of those ones where if you did this, the absolute value of it, it would look like it's converging to 1, but in this case it doesn't because of the, it's swapping back and forth. And that's actually, so if we look back, actually, that's very important. So if we look back at the rule, if we remember the absolute value rule, where is it? Where was the absolute value one? There. So remember, the limit of the absolute value has to go to 0. And in this one, when we do the absolute value, it's 1. So since it doesn't go to 0, the limit doesn't converge. Because that one would be going to 1 and not 0. Couple more. Now this one, we have -1 to the nth power, which by itself we know doesn't converge, but we're dividing it by n. So now if I look at this limit, now if I take the absolute value of this, I get 1 over n. Now 1 over n goes to 0. So since that goes to 0, then the limit of the original function also has to go to 0. So this function converges on 0. Let's look at a trig one real quick. So we've got sine of pi over n. Now, because the sine function is continuous at 0, basically it constantly goes there. So if we had sine of pi over, so then we could basically, since it's continuous at 0, we can pull out the sine. So I'm looking at the limit of the middle piece there. So the limit of pi over n, as n's getting infinitely large, that's going to 0. So this is really going to the sine of 0, which is 0. So that goes back to those rules where we can split things up and break things apart. I can actually look at the function inside of it as long as it's continuous at that value. All right. 10. Oh, okay. All right. So let's look at this one. So the next thing we want to do sometimes is figuring out which values of r are going to make a function convergent. Because if we can figure out this piece, I can then use this to do other problems, especially things that have powers. So if we're looking at r to the nth power, I want to know which values would go to infinity and which values would go to 0. So if we look at this, and actually you might have seen this previously, if the ratio is less than 1, but greater than 0, so it's between 0 and 1, that's going to converge. If the ratio is bigger than 1, it's going to diverge because those numbers are getting larger and larger every time. If it's a fraction, those numbers are going to get smaller and smaller as you multiply them to the powers. So that's obvious. We've done that. We've seen that before. Now the question is, what happens at those values? What happens at 0 and what happens at 1? So if we look at 1 to the nth power is going to equal 1 because it's 1 times 1 times 1. It's just always going to equal 1. And 0 to the nth power is always going to equal 0. So we now figured out that those values will actually converge to a specific point. The next thing we want to look at is what happens when we're less than 0, or the negative side of it. So 0 to negative 1, if we look at the absolute value of that, we take the absolute value, those are also going to equal 0. So because of that theorem we looked at before, where as long as the absolute value of that comes out to be 0, then those are also convergent. And the same thing happens if it's less than negative 1, then it's also going to be divergent. If it equals negative 1, what would happen at negative 1 with the powers? We looked at that one already. That one's the one that's going to flip-flop. It's going to go negative 1, positive 1, negative 1, positive 1. And we've already determined that one also diverges. So that's that case there and the ones. So we have this function here. We have the limit as n goes to infinity of r to the n is equal to 0 if if r is between negative 1 and 1. So any value between negative 1 and 1 for r is going to converge to 0. If it's 1, it's going to converge to 1. Everywhere else, it's going to diverge. So that ratio piece, that is going to help us a lot when we start looking at the series and so forth, because that's geometric series parts are the ones that are raised to a power. All right, one more thing with sequences. A sequence can be either increasing, if it's the next value is always bigger than the previous value. It can also be decreasing, if the next value is always smaller than the previous value. And if it's doing only one of those, so if it's increasing or if it's decreasing, it's monotonic. Not every sequence is monotonic because some sequences do go up and down. So you don't always have a monotonic sequence. But if it's going one direction, so if it's always increasing or always decreasing, we call it a monotonic sequence. All right, so if we look at this sequence, 3 over n plus 5, this sequence is decreasing. Because if we look at, we have the n plus 5 there, if we change that n to n plus 1, so that's going to be the next term, 3 over n plus 6 is less than 3 over n plus 5. That's how we would show that a sequence is either increasing or decreasing. We don't look at the numbers, we plug in n plus 1 or n minus 1 to figure out what the values are going to be in the next function. So you have to prove it symbolically if it's going to increase or decrease. Because if we prove it with numbers, it might work for those set of numbers, but another set of numbers, it might change depending on how the values get bigger and smaller. All right, so if we look at this one, we want to show that n over n squared plus 1 is decreasing. So to do that, I have to show that I have to change the n's to n plus 1s and have to show that it's less than the original function of n over n squared plus 1. So I change all the n's to n plus 1s and I'm going to solve it. So now, since I have n plus 1 over there, so I'm going to cross multiply. So I have n plus 1 times n squared plus 1. And we're saying that's still less than n plus 1 squared plus 1. Then, of course, I got to FOIL it all out. So I have n to the third plus n squared plus n plus 1 equals n to the third plus 2n squared plus 2n. Move all the terms over. So I end up getting 1 is less than n squared plus n. So the question is that true? Well, the smallest value for n is 1. And n goes up from there. So if n is 1, then 1 is going to be less than 2, which is true. And any value after that point is obviously going to be bigger than that. So since we know it works for 1, then that function is always true. Another way that we can do it, and one way that I personally like, is actually looking at it in terms of a derivative. If we take the derivative of that, remember the derivative is finding slope. So all I have to do is show that my slope is going to be negative, because if my slope is negative for that function, the function is always decreasing. And that's what derivatives help me find. So when I take the derivative of this function, I get n squared plus 1 minus 2n squared, or 2x squared over x squared plus 1 squared. Simplify that down a little bit, and I get 1 minus x squared over x squared plus 1 squared is less than 0. So the bottom is squared, so the bottom is always going to be positive. So all I have to do is figure out what values are going to make the top always negative. So as long as x is greater than 1, there, this top value is always going to be negative. And 1 was going to be 0. So as long as that top value there, that x is greater than 1, it's going to be a negative slope. Therefore, this function is always decreasing. This works really well as long as you can do your derivative quickly and simply. Does that make sense?
Yes.
Okay. All right. Last piece before we move on. If I have a bounded function, which means that function's going to stop at a specific value, doesn't matter what it's bounded by, but it's not going to go any higher than this number, and it's not going to go any lower than this number. We call that a bounded sequence. So it's not necessarily convergent because it can bounce back and forth, like the negative or the n -1 times or -1 to the nth power. It can bounce back and forth. That was still bounded, but it's still bounded above and below. If the sequence is bounded and monotonic, which means it only goes in one direction, then we do know that that function is convergent. Because if it's bounded above and bounded below and it's only going in one direction, it's going to have to hit. Worst case, it's going to hit my bound at the top or the bound at the bottom. So my limit at the max would be whatever the bound is. Or it could actually show up a little lower than that. But it will never, as long as it's going only one direction, it's always going to be bounded or convergent if it's bounded and monotonic. All right. Next, and there's a reason we're doing these together, because they're in essence, series and sequences are basically the same thing. The only difference between a series and a sequence is just a set of numbers. A series, we're doing something with those numbers. Well, most of the times, we're summing them. We're going to add them together. So here's pi. We know pi goes on forever. And when we look at it, we actually can calculate pi based on this setup. And the 3 dots just means it keeps going on forever. So I actually think that's higher now. So the book goes that the current record for computing the decimal approximation of pi was 10 trillion decimal places in 2011. I'm pretty sure it's higher than that now. So, but each of these values, we could take any infinite decimal or any decimal and actually write it as a series of sums just by putting the decimals over the powers of 10. So that's one way that we can get the value of an infinite or decimal, and we just sum it to get the actual value originally. So that's where the summation piece comes into play. So we looked at a sequence, so that's a sequence, and all a series is going to be doing is adding or doing the summation of that sequence. So those are really the only difference between the two. But that gives us some more actual calculation values and stuff like that. And it's one of the reasons why we really want to know if a sequence is convergent or divergent. Because if it's divergent, then my sum is going to go to infinity. If it's convergent, I might actually be able to get a specific value out of my series. All right. So here's the example of a finite sum. So it's 1 plus 2 plus 3 plus 4. But since I'm adding those numbers up, it keeps getting higher and higher and higher. That series right there is going to go to infinity. So if I was looking at an infinite series, it's going to infinity. However, I can find the nth term, and I also can find the sum of a finite set of series. If you ever heard, there was de Gauss, when he was a child in elementary school in the 1700s, his teacher decided, this is the story that goes behind it. His teacher decided to tell the class because the teacher didn't want to do any more work in the class. So he told the entire class to add up all the numbers from 1 to 100. Now, if you were in elementary school and you didn't have a calculator and your teacher told you to add up all the numbers from 1 to 100, most of you probably would start off at 1 and go 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and so on and so forth, all the way up to 100. Well, he didn't do that. He was a little smarter than his teacher at that point. He came up with a way to add those numbers together quickly to figure out what the series is. And what he noticed was if you do 1 plus 99, you get 100. If you do 2 plus 98, you get 100. So he figured out how many pairs of 100 there was, multiplied that out, and then added the 50 that was left in the middle. So ended up getting 5,050. So the teacher, figuring he cheated, told him to add up all the numbers from 1 to 1,000. And when he added up all the numbers 1 to 1,000 in about a minute, came back in and told the teacher kicked him out of school. His father actually happened to be the headmaster of the school and decided to pull him out of school because he figured he was too smart for the actual teachers at that point. So that was really we're looking at series and how series can be very powerful because it actually allows us to do massive calculations a lot quicker if we know how to actually break them down. And that n over n or n plus 1 over 2 is going to be a sequence that we're going to use quite often to do some calculations. Now, if we look at another one, so if we have this one, we have 1/2 plus 1/4 plus 1/8. This would be the series is that, and we would actually get a sequence. So if we did 1/2 and then we did 1/2 plus 1/4, we'd get 3/4. So we can see how this series here creates a sequence of partial sums. So if we're doing each sum, we're going to get a sequence out of it, which also allows me to come up with a function for it. If I come up with that sequence, and I can come up with the equation for that sequence, so the 1 minus 1 over to the nth over 2, that value there, and that 1/2 should be in parentheses at that point. If I came up with that one, I can now figure out what this converges to when I look at it as infinity. So we can look at this one. If I just did the 1 term, I'd go up to it's half. 2 is a quarter, and as I do higher and higher, 25th terms, now we're starting to get really, really close to 1. So we're looking at this series is going to converge to 1. So we have a series that converges as well. No matter what the function piece we're going to have, going to infinity, it's getting closer and closer to 1. And that's where we get the 1 over 2. So if you think about it, what we were just talking about a little bit ago with those ratios, if we had 1/2 to the nth power, that 1/2 to the nth power is going to converge to 0 because it's between -1 and +1. So since those numbers are getting smaller and smaller and smaller, the difference between the values are getting smaller and smaller, which allows it to actually do converging or convergence. So this is just looking at how they did the partial sums, which we just talked about. We just talked about convergence. If the sum of the series keeps going, so if the sequence is divergent, the series is also divergent because it would go to infinity. If a sequence is convergent and goes to a real number, then the series would also could be also convergent. So it just depends on where it converges to. It's got to converge to 0 for it to actually be a convergent series. All right. I want to look at example 1 real quick. So if we look at this series, and my series comes out to be 2n over 3n plus 5. So that's my series. We can do the same limit thing that I just did with my sequences to it, where we have the limit as n goes to infinity of 2 over 3 plus 5 over n. And that's going to converge to 2/3. So this series right here is going to converge to 2/3. So I would know that sequence or that series converges to the 2/3 because that sequence that I was looking at converges to 2/3. There is two different types of series. We can have an arithmetic series or arithmetic sequence. We also can have a geometric series or a geometric sequence. Arithmetic ones are addition. Geometric ones are powers or multiplication. And this is where that ratio, that common ratio we were talking about a little bit ago, comes into play. Because in essence, my geometric series is that r raised to a power of n minus 1. So that first term is always going to be the 1, because r to 0 is going to be 1. If r equals 1, it doesn't work because it's just going to keep adding the same number in front over and over again. It goes to infinity. If r is between, so if r does not equal 1, we're going to get this sequence here. So the sequence is a 1 plus r to the n over 1 plus minus, or 1 minus r to the n over 1 minus r. You're going to need that to do some calculations and stuff when you're looking at the functions. So I would make sure you knew that sequence. So for any geometric series, that's going to be the sequence value. Now, we know, so if this is my sequence, now we're going to go right back to my sequence or the sequence section that we were looking at before. When we're looking at -1 is r is between -1 and +1. And these values, that's going to be convergent. So r is between -1 and 1. This series or the sequence is going to be convergent, and therefore the series would be convergent. If my r is less than or equal to -1 or greater than 1, then the sequence is divergent, and then my series does not exist. So therefore the series diverges in those cases. So we get it down to that point there, and if the r is between -1 and 1, it converges, and its sum is always going to be a over 1 minus r. That's what it's going to converge to. If r is less than -1 or greater than 1, then it's divergent and it doesn't exist. So a geometric series, this is basically summarizing it all, is convergent if it's the absolute value of r is less than 1, and it's going to converge to a over 1 minus r. And it's divergent if the absolute value of r is greater than or equal to 1. A is your first term, so that would be whatever that first term is your a, and r is your common ratio that we're going to look at. So if we look at this series right here, this is a geometric series. So the first thing we want to find out is we want to figure out what our common ratio is. So what am I multiplying each term by to get the next term? So what do I multiply 5 by to get -10 over 3?
Would you divide the 5 by 10 over 3 to figure that out?
Yep, you can do it that way.
2/3.
Yep, it's going to be 2/3. Yeah, sometimes if you can't figure it out just by looking at it, yeah, dividing it would definitely work. And this one, you could look, it's pretty easy to look at and figure out that, okay, I'm dividing by 3 because the bottom's now 3, and then 5 times 2 is going to give you 10. And then what I do is normally, like, you look at the first two and figure it out, and then look and see if it works to give you the next one. So -2 times 10 is going to give you 20, and 3 times 3 is 9. So that does work. So my common ratio is -2/3, and my first term is 5. Now, does this converge or diverge? If the ratio is -2/3, that's between -1 and 1. So this series is going to converge. And since it's going to converge, we can then use that a over 1 minus r to figure out what it converges to. So I have 5 over 1 minus -2/3, which is going to converge to 3. So the sum of this infinite series is going to be 3. All right, let's look at this one. So in this one, I have a series, and it's 2 to the 2n, and then 3 to the 1 minus n. So now, in this series, I don't have necessarily something that makes a nice common ratio. So I've got to manipulate the problem a little bit to get a common ratio. So to do that, we want to start looking at the numbers. So if I have multiplication of exponents, I can split those exponents apart. So if we look at the multiplication 2 to the n, I can say 2 squared to the nth power, which means that's really 4 to the nth power. And then the 3, 1 minus n, I can flip that and make it n minus 1, because I want that n value to be first. And now a negative exponent puts it down the bottom. So now I'm at 4 to the n over 3 n minus 1. Does that part make sense? This is using those exponent rules to manipulate the function. Now, I want to get the top and the bottom to both be n minus 1. So if I want to do the top to be n minus 1, I have to multiply it by 4. So I'd have 4 times 4 n minus 1. Because then basically, if I put those back together, I'd have 4 to the 1 power times 4 to the n minus 1. So I'd do n minus 1 plus 1, which would give me back to the 4 to the n. And what that allows me to do is it then says both the 4 and the 3 are both raised to the n minus 1 power. So that right there gives me my common ratio.
So why does the 3, when you take the negative sign out of the n minus 1 and the powers on the 3, why is that negative and then n minus 1 still? Like, why isn't that n plus 1?
So what we're doing is we're actually switching it. So if you looked at the 1 minus the n, the 1 is positive and the n is negative.
Oh,
so
I
by
see.
pulling out the sign, I swapped them.
Okay.
And the entire, there's no, like, the only reason we're doing it is because I want to get the 3 in the bottom. So this way I can get a fraction.
Okay.
So it's one of those things, like, it's like there's no real reason to do it except for the fact that I can't get to what I need, how it's listed there. So by flipping it, pulling the negative sign out, now I have it in the denominator. And it also, in most of the problems that we look at, you want the n first. So by swapping it, now I have n minus 1 instead of 1 minus n. So now if we look at this, my common ratio is 4/3. So does this converge or diverge?
Can you explain how you got to that last step one more time?
The forward third to the n minus 1?
Yep.
All right, let me see if I can actually. So I'm going to try to write with my actual mouse, which is going to be absolutely horrible, but that's okay. So that right there becomes 4. Actually, you know what? I got a better way to do this because I can just type this. All right, so this becomes 4 times 4 to the n minus 1. Okay. And the reason why that works out that way, because if we look at it in terms of the exponent rules, this would be 4 to the first power times 4 to the n minus 1, which I could then put back together as 4 to the n minus 1 plus 1, which is just 4 to the n. So in essence, what I'm doing is I'm taking this and I'm going backwards to get the actual numerator, the power to be n minus 1. Does that make sense?
Yep.
Okay. And the reason I wanted that is because I wanted to get the n minus 1 on the top and the bottom so I could get a fraction. So I can get what that ratio was. And in this one, my ratio is 4/3. And since 4/3 is greater than 1, this series diverges. They also say the other way you could actually do it is if you didn't want to do it this way, you could just write out the first few terms and you'd get something very similar to what we were looking at in the last problem, where you have the actual sequence of values there, and then you could actually just look at it and figure out the way as well. But it's nice to be able to learn how to figure out how to do it mathematically or algebraically instead of just numerically. All right. Let's skip that one. All right, so the next thing I want to do is sometimes we want to be able to take a number, a decimal, and write it as a fraction. So that's a thing that's actually kind of important depending on certain jobs and stuff you're going to have to do. Taking a decimal and actually writing it as an exact fraction that can then be calculated out is useful. So in this one, now it only works on fractions that repeat. So you could not use this to find pi. You could not use this to find e because those are irrational and they go on forever. You could find it to a specific value of them. So like that's actually how they get 22/7, which you hear a lot of time for pi. And the reason why is because it's only doing a certain number of values of pi. It's not the whole thing. So I do 2.3 to the 1 or 1/7, and the 1/7 repeats itself. So we're looking at this. I want to write this as a set of fractions. Because once I write it as a set of fractions, I can then write it as a sequence, a geometric sequence, and then use that to figure out what the value is going to go to. So I have 2.3 plus 17/10 to the thirds, plus 17/10 to the fifths, plus 17/10 to the sevenths, and so on and so forth. So if I ignore the 2.3, so if we just take the 2.3 out of the situation for a minute and we just look at the 17s, I have a geometric series, and my first term is 17/10 to the third. And then for each one after that, I'm multiplying it by 1/10 squared. So my initial term is A, is 17/10 to the thirds, and my ratio, or my common ratio, is 1 over, in essence, 100. So first off, does this series converge or diverge?
Diverge?
Nope, this one converges because 1 over 100 is between -1 and 1. So as long as the ratio is between -1 and 1, it's going to converge, and this one definitely is. This one's 1 over 100. So that means I can use that equation, that a over 1 minus r, to do the calculations. That's really small. Let's see if we can make it a little bigger. All right, so remember I pulled the 2/3 out. My a was 17 over 10 to the third. And then I have 1 minus 1 over 100. So 17 over 10 to the third is 17 over 1,000. 1 minus 1 over 100 is 99 over 100. If I simplify that fraction down, I get 17 over 990. And 2.3 is 23 over 10. And we add those fractions together, and we get 1,147 over 495. So if you were to divide that in your calculator, you would get 2.31717171717, and it keeps going on and on forever. So that's one use case series and things to figure it out. All right. Let's look. Oh, that's right. All right. Let's look at one series that's actually used quite a bit. It's known as the harmonic series. The harmonic series is 1 over n. So this is a summation of 1 over n. So we want to figure out that we want to prove that this is divergent. So if I looked at 1 over n, I get equals 1 plus 1/2 plus 1/3 plus 1/4 and so on and so forth. Now, if you're quickly looking at this, you might think, well, that kind of makes sense that it's going to go to 0. So why wouldn't it converge? This is one of those interesting cases, and that's why this is a very special one known as the harmonic series. Let's look at the partial sum. So let's look at a specific set of them. So let's look at the second one. So the second one, I have 1 over 1 plus 2. So just the first two terms, I'd have 3/2. Now let's look at the fourth one. So the fourth one, I have 1 over 1 plus 2 plus 1 over 3 plus 1 over 4. Now, I could add those together, but let's make our lives a little simpler. We're just going to change the second 2 to 1/4. And I know that this term right here is bigger than this one, right? Everybody agree with that? Because I'm changing 1/3 to 1/4. Okay, so now this goes to 1 plus 2 over 2, so that goes to 2. And I know this is bigger than 2, but I know it's at least bigger than 2. But 2 is already bigger than 3/2. So I've already gotten bigger, and I know this one's even bigger than the actual 2. If we look at the eighth one, doing the same thing I just did in the last one, I get 1 plus 3/2, so I get 2.5. And I know whatever I originally had was going to be bigger than that. I look at the 16th one, now I'm at 1 plus 2, which is 3. So what I'm finding out is that every doubling, it goes 3, 4. The 32nd one's going to be 5. The fourth one's going to be 6. So this keeps getting bigger and bigger. So that my sum is going to be bigger than whatever 1 plus n over 2 is going to be. So since this keeps getting bigger and bigger, it goes to divergent. So even though those fractions are getting smaller and smaller, they're actually not getting smaller fast enough. And since they're not getting smaller fast enough, it diverges. The harmonic series is going to come back. We're going to use that in a lot of the calculus stuff that we're going to look at in section 10, 11.3, 11.4, and so on. So remember the harmonic series. So if a series is convergent, then the limit of that this sequence is 0. Okay, so if a series is convergent, I know that the limit of a to the a sub n equals 0. However, the converse of that's not true. If the limit goes to 0, we do not know if the sequence is convergent. And we just showed that why. Because if I did the limit as 1 over n goes to 0. But I just showed that the series is not convergent. So one way is true. If we know it's convergent, I know it's going to 0, but I can't go the other direction. One thing we can do, though, along those lines, is if my limit doesn't exist, or my limit is not 0, then I do know that my series is divergent. So what's known as the test for divergence, if we do that test, and I know that limit doesn't go to 0, or I can't find it, then I automatically know that the series is divergent and I can stop right there. I don't have to do any calculations for it. All right, one more problem and then we're done. No, these are just simple series ones, same thing as we were doing with the sequences. Yes, this one. All right, so we want to show that this series diverges. So all I'm going to do is look for the limit of this original function there, the n squared and 5n squared plus 4. So I'm going to divide them all by n squared. Dividing them all by n squared, I get 1 over 5 plus 4 over n squared. That 4 over n squared goes to 0, so this limit goes to 1/5. Since the limit goes to 1/5, it doesn't go to 0. Therefore, the series diverges based on the test for divergence.